Independence Day 2016. Juno reaches Jupiter and gets down tow work. The probe points its high-resolution camera at this stormy planet. Juno's photos don't let us down. The pictures flown back from Juno are simply beautiful. All of a sudden you have this gorgeous mosaic of this planet as a human being. I'm like, oh my gosh, look at this. This is amazing. This is coming back from Jupiter. These are the closest ever observations of Jupiter, a planet 500 million miles away. But we didn't launch Juno to simply take photos. One of its primary objectives is to look deep inside Jupiter's dark center. One of the major questions we have regarding Jupiter is, does it have a core? And you'd think, well, obviously it has a core, as all planets have a core. The Earth's got a core. So does everything. Except, as it turns out, Jupiter may not. Understanding what is at the center of a planet enables scientists to roll back the clock billions of years to the age off planets. If Juno can tell us what is at the heart of Jupiter, then it could transform our knowledge about how the gas giant came into being. If Juno detects a solid core, it might indicate Jupiter initially formed as a rocky Earth-like planet and continued to grow. But if Juno discovers no core, it might indicate that Jupiter bypassed the rocky stage and developed from a gas cloud directly. Solving this question could shed light on other enigmas. As well, if we can determine how Jupiter formed, we can determine the rest of the story off the solar system. So, how do you get down into the interior of a planet when all you can truly see are the very tops of the clouds? Well, amazingly, you can utilize a gravity. As Juno orbits Jupiter, it is able to feel in its orbit tiny little changes in Jupiter's gravitational pull. As Juno zooms around Jupiter, gravitational spikes pull on the craft. Turns out that some regions of Jupiter are denser than others. Jupiter were this solid ball. Then when Juno flies by it, as it flies quite close over its cloud tops, the path would be extremely smooth, actually. If Jupiter does have layers or regions where there's more mass and regions where there's less, then it's going to pull on Juno a little bit differently. Going over regions of dense mass gives Juno an acceleration boost. So what they do is the engineers back on Earth can essentially just kind of report how fast is it moving right now. How about now? How about now? And you'll build up a map off where the mass is in Jupiter below the spacecraft as it goes around. Juno's instruments start to chart the center of the gas giant, and they reveal the sensational core for the very first time. And what Juno discovered was this hapless mass, a nebulous thing in the middle of Jupiter. It's not as hard as we thought if it was just a metal rock core, but there is something in the planet's center. Juno finds hydrogen and rocky material dissolved, and mixed together, it's a new kind of planetary core. Astronomers call it fuzzy. We expected to see an avocado. What we saw was a bowl off Sheely. It's a hydrogen fluid chili con carne. None of our models of the interior of Jupiter worked. That means we have to start over from the drawing board. The idea is that Jupiter didn't form from gas or rocks, but from small pebbles smaller than an inch in width scattered all over Thensient. Solar system, 4.6 billion years ago. These pebbles aggregated together. They accreted into a huge body that was the kind of seed, the core of Jupiter. The cloud of pebbles bunched together to create one large core 20 times Earth's mass. But these pebbles can't hold this expanding world for long. At some point, we have to leap from those centimized bodies all the way up to real big things. It's like 100 kilometers planet decimals to really initiate growth of a world. As Jupiter expands, its hunger grows insatiable. The centers of other would-be worlds are pulled in by its massive gravity and are engulfed upon impact, causing Jupiter's center touch. Big chunks of incoming rock are blended up with gas and the pebbles that originally built the core. We think that the core material that might have been there is actually dissolved and mixed in with the rest of the planet. This mix of rock, gas, and pebbles leaves the core in a strange state somewhere between solid and liquid, or in other words, fuzzy. Once Jupiter's core reaches a critical mass, its gravity draws in all the surrounding hydrogen gas, constructing the Jovian atmosphere. trapping the fuzzy core below thousands of miles of dense clouds. And this is what created Jupiter the way we know and adore it today. Juno's revelations about Jupiter's fuzzy core may rewrite the textbook on Jupiter's early days. But Juno's just getting warmed up. We haven't even begun to the amount of mysteries there are. There's more to Jupiter than meets the eye. As Juno's instruments start to uncover a darker side to this jaunt world, Jupiter's atmosphere is one of the most cruel in the solar system. And that is due to its hugely powerful magnetic field, and Juno is right in the middle of it. The gas giant. Jupiter contains secrets to the mysteries of our solar system. And in 2011, NASA embarked on a billion of mission to reveal them. 3-to-1 ignition and liftoff of the Atlas V with Juno on a journey to Jupiter. In order to reach its destination, Juno takes 5 years. To send any spacecraft to another planet will be challenging, but to send one to Jupiter is actually pushing things quite hard. Juno navigates through the solar system with precision. The craft battles violent temperature changes and navigates carefully through the asteroid belt. If there's a fleck of dust in your path and that thing slams into your spacecraft, it can do significant damage, 7 billion miles into its mission. Juno finally nears its target, but the probe is hurtling towards Jupiter at 165,000 miles per hour. Juno is traveling very, very quickly. It's one of the fastest vehicles ever launched into space. You have to travel fast enough to arrive, but then slow enough to be caught by that planet's gravity. You have to make it just right. Orbiting Jupiter is the most difficult aspect of the mission. Do it incorrectly, and Juno might crash into the planet or drift off into outer space. To be able to get Juno into a stable bit about Jupiter is nearly the same as saying shoot a basketball from London and have it bounce on the front of the rim in New York and just sit there balanced. I could do it. But the red planet Earth's neighbor, and the target of NASA's most ambitious quest to this point. But this mission will be tougher than could have imagined. It pains us to consider how difficult it is. It's farther from the Earth than any human has ever been. We had to take every precaution as NASA astronauts reach Mars. They will encounter a massive challenge. It's a daunting task to land on the planet historically. Mars has not always extended the welcome. Mars is kind of like a graveyard for spacecraft. It's actually really hard to send something from Earth and land it on Mars. This is how the European Space Agency hoped its $250 million Skyo would touch down in 2016, but the lander systems got it wrong. The parachute detached early, sending the craft into free fall for 33 seconds. Skyo smashed into the surface at 335 meters an hour, leaving a deep black scar on the Martian surface. As it happens, Mars is actually a very hard planet to land on, even humanity's best and brightest engineers. We've got around a 50% success rate for landing on Mars. The red planet is covered with crashed spacecraft that didn't quite get it right, and for NASA's initial rough descent to Mars, the space agency will need to learn from these errors. But as the team struggles toward the surface, they're fighting the Sami Sioux as all the failed landers before them. The Martian atmosphere is 100 times thinner than Earth's, and therefore it can't supply the drag to slow down a spacecraft. So, it's not like the Earth, where you can have these huge giant parachutes that slowly bring you down to the ground. You can utilize some of the air, but it's difficult. The thin atmosphere of the red planet is an issue that's billions of years nth making. Mars doesn't have a big atmosphere because it's perpetually being stripped away, because there isn't the protection of a magnetic field. The solar wind can strip an atmosphere away. On our planet, a liquid metal core generates a magnetic field that protects the planet and keeps the atmosphere intact. Mars is not the same. 4.5 billion years ago, Mars and Earth were created by dust and gas in space. Mars develops rare materials. To build were limited. Its development was incomplete. And so Mars is much smaller than the Earth. It's about a factor of 10 smaller than the Earth, and that factor of 10 in mass is significant. All that extra weight keeps the interior of the Earth warm and to have a rotating core, which produces a magnetic field. 4 billion years ago, the whirling heart of Mars began to cool and solidify, and without a hot core, there is no magnetic field. being produced, all the high-speed charged particles emitted by the sun erode the atmosphere and gradually rip it away. We know it's leaking atmosphere every second because of the solar wind. So yaukno, bye-bye atmosphere. With not much Martian atmosphere to play with, NASA had to get innovative to deliver its screwless landers to the Martian ground. In 2012, the Sky Crane, the game-changing one, landed the Curiosity rover employing Guaracus and retro rockets. Prior missions have employed both a parachute and another device like a bouncy ball inflated around the spacecraft. I don't think a human crew is going to be very happy if they're going to be bouncing onto the surface and an air rolling to a stop. Right? Landing people on Mars is going to require some new tricks from NASA. The 2020 rover will solve the problem. With the innovative supersonic ratchet inflation research experiment, it will slow the vehicle down quickly with the power of an airplane jet engine. A human lander would weigh much more than 2,300 pounds rover. Supersonic parachutes wouldn't even deliver a crew safely to Mars. NASA will require a new plan. One suggestion is utilizing the thin Martian atmosphere in a special manner. There's this concept of coming in very fast, reaching the thick portion of the atmosphere, and then go horizontal to the ground and glide and lose your momentum that way. As the astronauts are descending, they tilt the nose of the lander to the Martian surface, to the thickest portion of the atmosphere near the ground. Then they make a last-second pull-up by utilizing friction from the atmosphere. Glow down the vehicle. Descent engines engage for final touchdown. Is that a nuts idea? I mean, yeah, it's a little bit strange. I don't know if we'd ever consider doing something similar, but I mean, you've got to be creative sometimes. At present, NASA's vision of landing a vehicle on Mars is still in the conceptual stage. But even if they manage to land astronauts on the ground, the thin atmosphere is far from finished with them. It produces rolling dust storms that blanket the entire surface of the planet. Mars does not merely have dust devils, it has dust hell. And these massive clouds have the ability to kill previously. When the wind brings this dust to a boil, it can be devastating. The actual issue is just that all of these fine particles are lofted into the air and it takes an awful long time for them to settle out again. What the dust is able to do is it just gets in the air and it hangs there, and just sits there. As additional material is blown into the air, it creates massive dust storms. The storms are so immense they have blocked the sunlight and chilled the Martian ground, establishing a temperature difference between the ground and air that makes the winds rise and the storms expand. And NASA's Opportunity rover knows firsthand the perils of being stuck in one. Building a planet. It's not an easy task to build a planet. With so many difficult steps in between, every single step, from dust grain to pebbles to planetesimals, takes time. If Jupiter had to wait until rocks in the distance bump into each other and merge, it would take 100 million years to be built. And that can't happen because Armature Sun ravages the gas in the protoplanetary disk. A gas disk around a star isn't going to last forever. The star is awakening and turning active. Time's running out. There's a young star in the center, and young stars emit violent outbursts of radiation. All types of solar storms blowing away the cloud. So if you're going to be a giant planet, you must act quickly. We know our protoplanetary disk only lasted around 4 or 5 million years. So we know Jupiter was complete forming just 5 million years into solar system history. And that means we have to jump-start that process really quickly and get Jupiter to construct a really large rocky core really quickly. Jupiter has to have a huge core of rock and ice so it can capture nearby gas in the protoplanetary disk. The planet must rapidly build its careen to capture this gas before it's blown away. To work out how Jupiter forms faster, we must wind back the clock to the earliest stages of planet formation. So in our protoplanetary disk, we formed our first planet. Tesimals, and we formed these out of all of the little pebbles that are out there in the disk. Now what's still around its neighborhood anthers? Just an enormous amount of those little pebbles everywhere. Throughout the disk, if we include these residual pebbles in planet formation models, things happen a whole lot quicker. Incorporating these pebbles into the mixture, incorporating this into the models was the giant key. These tiny pebbles can actually provide a lot of mass. It's these protoplanets that are growing. That's pebble accretion. And this is a way of actually speeding up the growth of early protoplanetary cores. Now, when a planetesimal forms, it no longer needs another planetesimal to grow. It can feed on the surrounding pebbles. So this planetesimal has some significant gravity. It can start grabbing nearby pebbles and growing, biocrating them. And this planetesimal has a huge reach because of how slowly these pebbles are passing on by. So it can stretch way out and capture a tremendous amount of pebbles super quick, and that'll improve its rate of growth. And this initial planet can grow super quick, consuming all the pebbles in the neighborhood. It's a feeding binge. Through overindulging themselves in pebbles, planets can develop 1,000 times quicker than through planetesimals alone. But when we model the solar system formation using pebbles, something unusual occurs. Pebble accretion, when we model it, it can be so effective and so quick that few simply begin with a disk filled with pebbles, and they begin forming planetesimals. Each planetesimal could grow to be something like the size of the Earth really quickly. Rather than accreting into giant planets such as Jupiter, you'd accrete into 100 smaller planets such as the Earth. And this isn't obviously what we're observing. So there's something else that has to be happening. In order to explain the formation of the solar system, we must consider how the planets that are growing interact with each other. So your first object in your disk that begins growing by pebble accretion is going to develop really quickly. But the next thing is attempting to develop out off the same disk. The same pebbles, but it's developing in close proximity to the first one. As baby worlds expand, they get more gravitational pull. Big protoplanets push around their smaller neighbors. This really big neighbor can disturb its orbit, can rattle it back and forth, and by lifting them up and out of the disk, they can effectively starve them, prevent them from reaching all of Thospobilsons, being pushed out of the disk full of material. The smaller protoplanet starves, the bigger protoplanet survives, feasting on pebbles and getting ever larger. Pebbles explain why outer planets outsmart the clock and develop before the sun blows away. The protoplanetary disk, we estimate that by accreting from pebbles, Jupiter and the other gas giants developed in only a few million years. When we put pebbles into our numerical simulations, our theoretical simulations, we are able instantaneously induce these growth mechanisms on those observed timescales. Pebbles allow Jupiter to develop into the largest planet of the solar system. It can coalesce into the kernel large enough that it would very quickly begin to consume the surrounding gas and become the Jupiter that we know today. The surrounding gas to an infant planet not only nourishes its growth, it can propel it through the infant solar system, which is bad news, because giant planets in motion equal disaster for other developing planets. July 2019. We find 4 unusual planets: WASP 178b, 184b, 185b, and 192b. All 4 are gas giants. They're in the sense that they orbit around their host stars at least 4 times closer than Mercury orbits our sun. The physics on this are extremely clear. You can't create a planet that close to its star. You simply can't get the gravity to pull enough material to do that. Thester and Turfris twisted. Stellar winds. Radiation. And the immense gravitational pull of a star should prevent any planet from forming where a WASP planet's orbit. But looking around the Milky Way, there are hundreds more giant planets orbiting just as close to their stars. It happens so often that it really took us back to the drawing board to understand what could actually drive that process. Planets can't develop so close to their stars, so we believe they develop elsewhere and drift inwards. That wandering of planets occurs in the earliest phases of planetary evolution, when that disk of gas and dust out of which the planets developed is still present. These gas disks are heavier than all of the planets combined. There's tens of thousands of Earth's masses of gas, and those gases interact and push and pull in the planets where there's a lot of force. And then as the planets get bigger, they open up a gap in the disk and you form kind of an inner disk in the gap where the planet is, and an outer disk. If a planet forms a gape and the gas can't pass through, all that gas accumulates behind it and just pushes. So you have thousands of times more mass than your planet pushing on your planet. It's like putting something in a flood and it's just going to vomit and push it downstream. The planets are just getting pushed downstream towards their star. Could a migrating planet be responsible for one of the greatest mysteries of this stellar system? Galactic neighborhoods, Earth carries us on a wild journey through the cosmos. And hints at the impact of this journey are lurking in our own backyard. Amongst the skyscrapers and traffic of New York City, we have moraines, rocks deposited by receding glaciers, 18,000 years ago. Manhattan was blanketed with a sheet of ice that towered above any skyscraper. Ice ages have regularly visited Earth's past, freezing our planet solid. There was a time in the history of Earth a few 100 million years ago. It's a snowball, Earth time, when we experience a very extreme glaciation. If you can imagine, a very extreme ice age. When we suspect that the whole planet was blanketed by an ice sheet. The trigger. Earth's orbital waltz around the sun. We like to imagine ourselves sitting relatively still on the Earth. It's very reassuring, actually. But we're actually revolving around the sun at around 66,000 miles per hour. The Earth covers more than 1.6 million miles in a day, traveling around the sun. This orbit isn't always interrelated around. Earth is typically going around the sun in, more or less, a circular trajectory. But over time, the massaging of this orbit from the sun, from the moon on the sea, Earth's orbit causes the orbit of the Earth to change. So that sometimes it's an ellipse. Sometimes it's more of a circle. Right now on the Earth, we're in kind of the most circular time in the orbit. NASA will need a new plan. One idea is to use the thin Martian atmosphere in a unique way. There's the idea of coming in really fast, getting to the thick part of the atmosphere, and then going horizontal to the ground and gliding and losing your momentum that way. As the astronauts descend, they tilt the nose of the lander towards the Martian surface, aiming for the thickest part of the atmosphere, as close to the ground. Then they pull in at the very last moment by utilizing friction from the air to slow down the vehicle. Descent engines ignite for the final landing. Is this a ridiculous concept? I mean, yeah, it's kind of strange. I don't know if we'd actually consider doing something like that, but I mean, you have to think outside the box sometimes. Currently, NASA's visions for landing on Mars missions are still on the plans. But even if they manage to land astronauts on the planet, the thin atmosphere isn't finished with them. It produces swirling dust storms that blanket the planet's entire surface. Mars doesn't only have dust devils, it has dust hell, and these massive clouds have been deadly before. Asterisk, when the wind kicks up this dust, it can have catastrophic effects. The actual issue is just that all these nice particles get lifted up into the air, and it takes a very long time to settle out again. And what the dust does is it just gets up in the air, and it just stays there and stays there. The more material that gets lifted up into the air, the bigger the dust storms are. The storms are so massive, they cover the sun and chill the Martian surface, producing a temperature gradient between ground and air that makes the winds speed up and the storms send large. And NASA's Opportunity rover, its first experience with the risks of getting stuck in one, building a planet, it's no simple task. Building a planet with lots of tricky phases in between, each one of these processes from dust grain to pebbles to planetesimals takes some time. Jupiter wouldn't have been able to wait for rocks far away to crash into each other and merge, because it would take 100 million years to form. And that can't happen because Ariathful's sun is aggressive towards the gas in the protoplanetary disk. A gas disk around a star can't exist indefinitely. The star is lighting up and getting active. The clock is ticking. There is a young star in the center, and young stars emit violent bursts of radiation, all types of solar storms blowing the cloud away. So if you want to be a giant planet, you must act fast. We do know our protoplanetary disk lasted only some 4 or 5 million years. So we do know that Jupiter was complete with only 5 million years of solar system existence, which means we need to jumpstart that process and get Jupiter to form a huge rocky core very quickly. Jupiter needs a massive rock and ice core in order to sweep up surrounding gas in the protoplanetary disk. The planet needs to quickly form its careening sweep up this gas before it's lost. To figure out how Jupiter develops quicker, we have to turn the clock back to the beginning of planet development. So in our protoplanetary disk, we created our first planetesimals, and we created these from all of the small pebbles that are out in the disk. Now what remain around its neighborhood and everywhere across the disk are a tremendous amount of those smaller pebbles. When we include these residual pebbles in models of planet formation, it happens quite a bit quicker, including these pebbles. In the equation, including this in the models was the key thing. These small pebbles are actually able to add a tremendous amount of mass to these accreting protoplanets. That's called pebble accretion. And this is one way of actually speeding up the growth of early protoplanetary cores. Now when a planetesimal forms, it no longer needs another planetesimal to grow. It can feed on the surrounding pebbles. So this planetesimal has some significant gravity. It can start grabbing nearby pebbles and growing biocrating them. And this planetesimal has a huge reach because of how slowly these pebbles are passing by. So it can extend way out and scoop up a giant amount of pebbles very quickly. And that'll make its growth rate even bigger. And this initial planet is able to grow extremely quick, consuming all pebbles around it. It's a feeding frenzy. By stuffing themselves with pebbles, planets can develop about 1,000 times quicker than with planetesimals only. But when we use pebbles to simulate the formation of the solar system, something strange occurs. Pebble accretion when we simulate it. It can be so efficient and so rapid that if you simply begin with a disk filled with pebbles and they begin building planetesimals, each planetesimal could grow into being something like the size of the Earth pretty darn quickly. Rather than creating huge planets such as Jupiter, you'd create 100 smaller worlds like the Earth. And this is obviously not what we're observing. So there has to be something else happening. So in order to figure out how the solar system was formed, we have to consider how the developing worlds interact with one another. So your initial object in your disk that begins accreting by pebble, accretion is going to increase really fast. But the next thing is attempting to form froms. Same disk, the same pebbles, but it's growing close to the first one. As baby worlds grow, their gravity gets stronger. Bigger protoplanets intimidate their smaller neighbors. This really large neighbor can disturb its orbit, can wiggle it up and down, and by bending them up and out of the disk, can effectively starve them, prevent them from reaching all of those pebbles smaller protoplanet starves. The larger protoplanet flourishes, feeding on pebbles and becoming increasingly large. Pebbles shed some light on how outer planets outsmart the clock and form before the sun disperses the protoplanetary estimate that by accreting from pebbles, Jupiter and the other giant planets accumulated on only a few million years. When we put pebbles into our mathematical models, our theoretical models, we can immediately make these growth mechanisms occur on those observed scales. Pebbles assist Jupiter in becoming the solar system's largest planet. It can grow the core large enough that it would quickly begin to consume the surrounding gas and become the Jupiter thought we observe today. The surrounding gas of an infant planet not only nourishes its growth, it can propel it through the infant solar system, which is bad news. Becko's moving giant planets mean disaster for other developing planets. July 2019, we find 4 odd planets: WASP 178b, 184b, 185b, and 192b. They're all gas giants. They're unusual in that they orbit their parent stars at least 4 times nearer than Mercury is to our Sun. The physics there is quite straightforward. You can't create a planet that near its star. You simply can't achieve the gravity to pull in enough material to do it. The star interferes with it. Stellar winds, radiation, and the immense gravitational pull of a star should prevent any planet from forming where it's the WASP planet's orbit. But looking around the Milky Way, there are hundreds more giant planets orbiting just as close to their stars. It happens so often that it really took us back to the drawing board to understand what could actually drive that process. Planets can't develop so near their stars. So we believe they grow elsewhere and drift inwards. This planetary drifting occurs during the very beginning of planetary formation, when that disk of dust and gas from which the planets developed is still present. These gas disks are more massive than all of the planets combined. There's thousands and thousands of Earth masses of gas, and those gases interact and push and pull in the planets with powerful force. As planets get bigger, they cut a gap through the disk, and you form sort of an inner disk in the gap where the planet is, and an outer disk. So if a planet cuts a gap and the gas can't pass through, all of the gas accumulates behind it and just pushes, so you have thousands of times more mass than your planet pushing against your planet. It's like placing something in a flood and it's just going to batter it and force it downstream. And the planets are just getting forced downstream too. Their star. Could a wandering planet be behind one of the biggest enigmas of the solar system? Galactic neighborhoods? Earth takes us on a bumpy ride across the universe. Clues to the impact of this journey are lying in our own backyard. In New York City, between the buildings and cars, we see marines, glacial rocks left behind 18,000 years ago. A wall of ice, higher than any skyscraper, blanketed Manhattan. Ice ages have hit regularly throughout Earth's history, placing our world into deep freeze. There was a time in the history of Earth some 100 million years back, the snowball Earth, stage when we experience a highly extreme glaciation, if you will. A highly extreme ice age, when we believe perhaps the whole Earth was blanketed with an ice sheet. The cause: Earth's orbital waltz around the sun. We like to imagine us sitting cross-legged on the Earth. It's quite reassuring, actually. But we're orbiting the sun at approximately 66,000 miles per hour. Earth moves more than 1.6 million miles a day as it orbits the sun. This orbit isn't always totally round. The Earth is typically orbiting the sun in more or less of a circle orbit. But over a period of time, the massaging of this orbit from the sun, from the moon along the Earth's orbit to make the orbit of the Earth, deviate. So sometimes it's an ellipse, sometimes a little more of a circle. Currently, on the Earth, we're in sort of the most circular phase in the orbit, so that would make the summers fairly mild and the winters fairly mild. But think about not too far back in history. It could have been quite dramatically different. When the Earth is slightly closer to the sun, perhaps you have a very hard summer, and then when you're on the other side of your orbit, you're slightly more distant from the sun than usual, so you have a very hard winter. Our environment is extremely sensitive to all these kinds of things. And when Earth's orbit is elongated, the actually can kick off an ice age. The Earth's 100,000-year orbital period led to the ice age that covered New York, and ice ages have had a profound impact on human history. 15,000 years ago, sinking temperatures trapped water away in ice in glaciers' caps, sea levels fell, forming land bridges between continents. Humans walked from Asia to America, and America was populated for the first time, May 2018. Scientists unveiled a whole new dynamic to Earth's journey. Every 405,000 years, our planet's orbital journey stretches to the limit, and Earth's planetary neighbors are guilty. Because Jupiter is the largest planet in our solar system. It's in a lot of ways the playground bully, right? Its dynamics, its gravity shapes a lot of the dynamics of the solar system. It actually pulls and does things with the Earth's orbit. It's accountable for some of the very changes that propel a climatic cycle. Here on our Earth, Jupiter isn't the sole playground bully. Music Venus is a pretty large planet, roughly the same size as the Earth, and it also orbits closest to us. So these two planets add just a teensy tiny elongation to our Earth's orbit. And as this cycle goes on, the more 30 minutes and 24 seconds, the more extreme it is. Or we can actually observe a temperature difference that occurs once every 405,000 years. Jupiter and Venus gang up on Earth gravitationally, tugging Earth's orbit into an even larger ellipse. Our planet's warm weather gets even hotter, and its cold weather becomes much colder. Today, we're in a moderate phase of the cycle. But in just 60,000 years' time, we could dip into another deep freeze. It's a little bit like a cosmic butterfly effect. I mean, even the smallest effects can have, big influence over time. Earth's orbit around the sun is just part of our far larger cosmic journey. The entire solar system is hurtling around the Milky Way, taking us places we don't want to be. Sometimes our planet might wander into what's essentially a bad neighborhood. What threats are in store for us? And might these suburbs be doomsday for life on Earth? In the past 3.7 billion years, a series of catastrophes extinguished nowadays 95% of all Earth species. Now, scientists believe our planet's orbit is at least partially responsible, but not the Earth's orbits around the sun. Our planet's bigger and longer circumnavant of the Milky Way. Our solar system and our sun is firing across the galaxy at around 537,000 miles per hour. Around the center of our galaxy, and the center of the galaxy is roughly 26,000 light-years away. So it would take the sun roughly 230 million years to make one complete orbit around the center of the galaxy. Even though going around the Milky Way at 500,000 miles an hour, Earth has made fewer than 20 circuits of the galaxy in our planet's total history. And it just so happens that this galactic journey is more complex than it appears. Now, if you trace Earth orbiting the sun, it creates an ellipse, but it's a two-dimensional figure. You think, well, the sun likely revolves in a plane too. It just happens not so straightforward. Most of the mass of the solar system is concentrated in the sun. So, Earth and the other planets smoothly orbit our star, but the mass of the Milky Way is spread out unevenly. That changes the gravity of the galaxy, and so it changes how things move in it. And in fact, if you give something a little bit of an up and down motion, it'll bob up and down as it circles. Riding the Earth is not much different than riding a carousel. When the sun and the Earth circle around the galaxy, the sun will also travel up and down like you're on one of those horses that has the pole. What this can do is transport us into various galactic environments. This bobbing motion carries Earth and the solar system on a 60,000-year ride up and down along the galactic plane of the Milky Way. Our orbit also carries us through various galactic neighborhoods, the moon's violent past. In 2018, planetary scientists were searching for hints about the moon's violent history. They examined maps from the Lunar Reconnaissance Orbiter and concentrated on dark spots on the moon called lunar rays. The terms we have for things we can observe on the surface of the moon are such as Sea of Tranquility. And so prior to our knowing what they were, astronomers would refer to this and say, well, they resemble oceans and seas. And that's how they referred to them, a reference to sea. And so you have Mare Tranquilitis, which is the Sea of Tranquility. But they're not seas of water. They're seas of lava, more than 3 billion years ago. The moon was blanketed by large seas of lava, nourished by massive eruptions of magma. These spots that we observe on the moon were lava eruptions, which have filled in these basins. These are hundreds of miles wide. These are gigantic, much bigger than even the largest volcanoes on the Earth. If you were on the Earth 3.5 billion years ago, you'd probably see the glow of the individual lava flows flowing out across the surface off Mare. We can work out how much lava flowed across the moon by measuring the lunar seas. But that's not all. The amount of lava in the seas can tell us if our planetary twin had an atmosphere. Volcanoes on Earth actually don't just spew out lava. Literally, gas below the ground comes out as well, and you have sulfur gases and carbon monoxide and lots of other things. Well, the same kind of thing occurred on the moon as well. The old lunar lava flows show that the surface of the moon was blanketed in lava for hundreds of millions of years. The largest eruptions occurred at 3 and 12 billion. Years ago, they buried the moon in 200,000 trillion cubic feet of lava. We calculate that there was enough lava emitted to blanket all of the continental United States to a depth of a 4-mile in lava. A total of about 3 billion cubic feet of lava flowed out of the moon's volcanic cracks annually. These great eruptions also released roughly 10 trillion tons of gas, such as water, vapor, and carbon monoxide. It would be sort of a hellscape of erupting. Lavas and then toxic gases would be spewing out of volcanoes. So all of this eruption of huge amounts of lava likely would have formed an atmosphere around the moon. It's still quite thin compared to Earth's atmosphere. but perhaps something in the order of perhaps 1.5 times as dense as Mars's atmosphere today. There might be just enough pressure there to be able to maintain water in liquid form on the surface, having an atmosphere surrounding the moon. Water vapor cooled and formed pool-soft liquid water. The fragile atmosphere retained heat, keeping the water from freezing, making it a harsh but possibly habitable world. 3 billion years ago, life existed on Earth. Is it plausible that the moon had it as well? This is not something that we have a load of data regarding. But it's possible because the moon definitely did have a lot of volcanic activity that might have created an atmosphere. So it is not a wild idea to consider there. It was a period of time when the moon was inhabited, but the warm, moist lunar climate did not persist. When the lunar volcanosity replaced the atmosphere, ceased to erupt. The moon's low gravity was unable to retain the atmosphere. Within a few million years, it was all lost. The surface water was lost to space. Temperatures dropped. Any life was killed, although the Earth and the moon began almost the same from this home disastrous collision. Over time, they spread increasing light and went on different paths of life because the moon was small and cooled down. The Earth was huge, was capable of sustaining an environment, capable of sustaining liquid water. The moon received none of that because it was just too small. We believed the small size of the moon would mean it cooled its molten core rapidly, extinguishing the volcanoes and halting the core from producing a magnetic field. But recent research indicates we might have made a mistake about lunar history. In 2017, we reanalyzed 1 billion-year-old moon rocks gathered by mission Apollo 15 and found something peculiar. The rocks contained traces of a lunar magnetic field. Billions of years passed when the moon's magnetism would have ceased to exist. We have a bit of an enigma here. When the moon was molten, it could maintain a magnetic field. But the moon froze up, and when it cooled, it would have extinguished rapidly its magnetic field. But samples from the Apollo mission brought to light that the magnetic field persisted longer than what believed took for the moon to cool down. We believed the moon lost its magnetic field 3 billion years ago, but the Apollo 15 rocks indicate the moon had a magnetic field 1 billion years ago, deep within the Earth. Scientists probe something mysterious deep within the Earth. It's a long-buried clue to our violent past. Deep down, 1,800 miles down below the surface of the Earth, our core is wrapped in liquid rock. But within that 600 miles tall and thousands of miles wide are yet two heavier areas, and they sort of cup the core of our planet. Like two hands, one of them, is half the size of Australia, for goodness sake. So, they're huge blobs down there. There's no reason they should exist. It is a mystery to us. In order to unravel this mystery, scientists must look at the rocks hidden more than 1,000 miles deep beneath the surface. We don't actually know what these two large rocks are composed of just sitting there on the core, but we've managed to sample it. How in the world can that be? Well, these blobs are really supplying mantle plumes which are ascending through the mantle. So volcanoes at Iceland and Samoa, for example, will bring up some of these chunks of rock from the mantle. It's a valuable opportunity for us to get a sample of some off that lower rock which we would otherwise never get to look at. These rocks are ancient, extremely ancient. It happens that the samples in Thelava, which we believe are from these clumps of rock in the mantle, are 5 billion years old. That is as old as the Earth is. So they do tell us something about how the internal composition of our Earth was. Set up in the very beginning days, off the Earth formation. So obtaining samples from that era is highly, highly significant. The rock's age could be a hint at where they came from. They are from an era of monstrous cosmic chaos, 4.5 billion years ago. The solar system was still a rather untamed place. We're getting to the end of planet forming. Earth would still be accumulating. Then, you might not recognize the Earth. In fact, you would not recognize the Earth at all. For instance, no moon. The Earth had no moon when it formed. The early Earth circles the Sun with other baby planets. One of those is an object that scientists have named Theia, and it's heading for collision with our home. The collision of Theia would have been a spectacular sight. It would have been one of the coolest things you could ever see in the formation of the solar system. Definitely the largest event in Earth's history. The Theia event is one that totally remade the Earth. The planet that the Earth was before the Theia event is gone forever. The impact melts rock and throws out over 1 billion tons of debris. During this incredible collision, these two planets were literally broken apart and combined into one big planet. Huge chunks of these stayed together as the now molten Earth began to form anew. Now we can kind of paint a picture of where these big lumps of rock might have come from. They're very old. They're in fact the same age as that large impact event. They could be pieces of Theia. The giant slabs of Theia sink down into our planet and lie undiscovered for billions of years. Earth reforms from the ruins of both planets. Now, you may think that this collision is just horrific. There's no positive at all. But there are a few things that resulted from this collision which could have produced the potential for life. When these two planets collide, portions of Theia's iron core are incorporated into Earth's. So, that's to say that Earth gathered a much larger core than it may have had on its own. That's good news for us because the center is the origin of the magnetic field that shields us. Liquid metal circulating around in Theia core creates Earth's magnetic field, a shield from the sun. The sun actually has the ability to emit billions of tons of high-energy protons and electrons in one burp, that ultimately would have stripped our atmosphere away. If it were not for that energized core and that magnetic field, we would appear to be like Mars, just kind of a naked and desolate desert. Due to Theia's excess iron, Earth's molten outer core is big, so it cools down slowly, remaining molten, and continues to produce a powerful magnetic shield. Due to that collision, the excess iron, the excess heat, we've remained active. We possess a magnetic field. We are a shield. And, as a matter of fact, that's why we're here discussing it. The devastating effect benefited life in other ways. The event was completely massive or not, an effect like a 100-mile asteroid that makes a large crater in the desert. But a planet. Colliding with a planet having a gigantic disk of wreckage spread out from the Earth from which the moon was created, the Earth becomes tilted on its side and rotates extremely rapidly. A day takes only a matter of hours. The Earth itself is tilted slightly on its axis, and if left to its own devices, would indeed undergo unstable, chaotic wobbling. The presence of the moon stabilizes the Earth, stabilizes our climate. The moon's gravitational attraction on our oceans causes tides and decelerates Earth's rotation, making it a world ready for life. We actually owe quite a lot to the moon. And Theia, its parent, for creating Earth a welcoming planet for life. The giant collision 4.5 billion years ago is sound like a disaster, but it may have been the best thing that ever occurred to the Earth. Theia, I would shake your hand because we owe you a lot. We also owe science about chance because we got lucky with a 1 in a million blow. Had the blow from Theia been slightly more forceful, the Earth might not have bounced back as well as it did, and we might not be here today discussing it. Had it been slightly less forceful than Theia influence, of it might not have wrought the changes that we believe were necessary for us to exist now. We happen to get lucky. Most planets don't get to make it through a crash like that and receive a free bonus moon in the bargain. Earth's colossal crash into Theia wasn't our planet's initial close call. A previous explosive encounter might have ended the solar system from igniting into existency and the Earth itself from taking shape. Saturn has an enormous diversity of moons. From Titan, a planet-sized moon, to things the size of a sports stadium. There has to be something extraordinary that occurred too. We've developed a system so intricate and evolving right before our eyes to comprehend such a marquette size difference. Scientists try to find clues in the moon's orbits around Saturn itself. Most of the moons of that system orbit in the same direction. Well, that's clearly not an accident. That's motion residual from the process of formation of our solar system. This indicates the moons formed approximate at the same time Saturn. Formed 4.6 billion years ago, the ringless gas giant forms from gas, rock, and ice in the protoplanetary disk with the familia of moons. This origin scenario holds for most of Saturn's moons, but not the newly discovered objects, revolving in the opposite direction of the planet's rotation. If there is a moon revolving in the other direction, it couldn't have developed with the planet. It must have originated elsewhere. Saturn captured those moons, but where? We believe there was a massive disturbance in the solar system more than 4 billion years ago, and the giant planets transitioned from a tightly packed and close arrangement began, interacting with one another, pushed each other around to end up in orbits that they occupy today. In the process, many smaller objects, such as asteroids from the outer region off the solar system, were scattered in all directions. In this early turmoil, Saturn captures some of the objects scattered about. Many bodies now fill the space around the planet, and that implies collision. Some of them are destroyed. Some create new moons. Some moons in the cosmic pinball get ejected from the system. Others to Saturn. There is only one big moon that makes it through the killing. Then suddenly, most of the mass of all the satellites is in this one moon. Titan. Titan could have coalesced out of material in the protoplanetary disk around the same time as Saturn. Then fed on the remains left in the subsequent lunar collisions, it gained 96% of material that orbited Saturn. It became so massive that it acquired a dense atmosphere. When Voyager took a photo of Titan, it was quite evident that Titan possessed a dense atmosphere. So incredibly exciting. However, it was so dense and opaque, this was all we could perceive. 20 years since Voyager, the Huygens probe from Cassini dove into the dark depths of Titan's atmosphere. Our initial images of what the Titanic landscape was like were completely and totally mind-blowing. Music it revealed there were mountains, and there was some sort of erosion on those mountains that appeared like liquid had flowed down the mountains and carried material with it. That liquid had to have originated somewhere. And where else but than rain than weather on Titan? We've only discovered 2 worlds in the solar system that have rivers and rain, Earth and Titan. Out of all this thick darkness, this is the most Earth-like place we've ever seen. Like, but not Earth. That rain that fills lakes and rivers on Titan is not water. It's liquid methane. It's like if every oil well, if ever a gas station on Earth began leaking everywhere. That is what we find on this planet. The methane is liquid on Titan because the surface temperature is 290 below zero, which is a huge issue for life as we know it. We do not know of any organism that can actually survive beyond -4°F, and that's just because cells will tend to freeze ether. The cells that we have, what they're composed of, these proteins and fatty material, stop functioning and all would perish. That's what happens with Earth's water-based cells. But would methane-based life fare in an extreme chill? The ALMA telescope found a lead in Titan's nitrogen and methane-laden atmosphere. With sunlight illuminating the atmosphere of Titan, things such as methane and nitrogen can be broken down and reformed like playing with Lego blocks, and then these molecules reassemble to form new ones, such as vinyl cyanide, artists' representation music utilized on Earth to produce plastics. Vinyl cyanide is able to form long chains of molecules, the kind that you would have to construct cell membranes, but in contrast to Earth's water-based cells, the below-freezing temperatures would not kill them. It would be able to withstand those low temperatures. So on Titan, it would be thought this vinyl cyanide can create the membranes needed for cells to grow, needed for life to occur. And the good news, plenty of this stuff is present on Titan today. Up to 10 billion tons of this vinyl cyanide in just one of Thalax. If you are ready to begin creating creatures from it, like, I don't know, giant squid. Do you enjoy giant squids? I hope so, because you could create billions of giant squids out of this vinyl cyanide. Saturn's geyser moon Enceladus might harbor life as we know it. Titan might have something completely alien. It is an unrelenting, harsh, cold world compared to Earth. But for Titanic life, it might just be ideal. As we search for life beyond Earth, it still comes with a bias of life as we know it. And so, it's great as we continue to explore and continue to evolve our definitions. We can expand our view of how to search for life. Maybe the Saturn system has 2 living worlds, but for life to thrive on Titan's surface, it must survive a storm of deadly particles, speeding away from the sun at more than 1 million miles.